So whoever still wants to do it, please do it. Please let me know by Tuesday, okay? And the following I already grabbed: Quench-Trap model, and the fractional Fokker Planck equation, and the paper of Derrida. They are already fully occupied. Okay. So So now one of you guys asked to do a project on fractional equations. So you will be lucky because I'm going to talk about this now a little bit, only a little bit. So generally speaking, what are these fractional diffusion and Fokker Planck equations? These are equations that use fractional calculus. What is fractional calculus? You know that in physics there are many applications of ordinary calculus, which means that you take a derivative of order 1, of order 2, of order 3 of some function. There are differential equations which use this, of course. But already from the beginning of calculus, Leibniz and all these great guys, all the mathematicians, they ask what is, let's say, a half derivative of a function. So roughly speaking, what is this thing? dt, let's say, to the half of t. What is it? So you know what is dt, let's say, of t to the n. That will give you something tn minus 1. So if you have this dt to the half, then this is the power 1 here. So maybe this is something like, you take the 1, you subtract. Here you subtracted 1, here let's subtract half, so 1 minus half, you get this thing. So it's very intuitive. I'm sure all of you thought about fractional derivatives when you learned ordinary derivatives, because you always have these full derivatives. And all the mathematicians, many mathematicians, Riemann, Liouville, Cauchy, all these people, they dealt with it in the mathematical literature. In physics literature, there was not so much to do with this, but it turns out, and that was an event that happened roughly 20 years ago, in particular, more or less, for a period of 10 years, it was a little bit hype, that we can describe certain aspects of the anomalous diffusion with diffusion equations that have in them fractional order derivatives instead of full order derivatives. And in particular, this is related to the continuous time random walk. So you know that ordinary random walks in the long time limit are described by Gaussian propagation of a packet of diffusing particles. Similarly, if you have continuous time random walk particles, let's say described by subdiffusion, then you have also a packet which is spreading, but with very non-Gaussian propagator, described by Levy statistics, actually. We showed this in the class. The mean square displacement goes like t to some power alpha. Alpha is less than 1. And then one can show, and this is what we're going to do now, that this can be described instead by a diffusion equation, which is the normal thing, or by a Fokker Planck equation. Again, that's again the normal thing. We can use, instead of the ordinary derivatives, we can use fractional derivatives. And that will describe the packet of particles in space. One can ask, why do we need at all diffusion equations and all this? This is maybe, I don't know if you thought about this question, because I mean, if you have a random walk, if we can solve it and we know it's a Gaussian, then why do we need at all a diffusion equation? Of course, the diffusion equation, the ordinary diffusion equation, is very useful because we can add to it boundary conditions, like what happens at large x. You have reflecting boundary conditions, you have absorbing boundary conditions, all kinds of boundary conditions which are much, much easier to solve with a differential equation if you compare with a random walk description. So most of the description is not based on a random walk description. If you have some application, Instead, people use this diffusion equation or the Fokker Planck equation with relevant boundary conditions to solve this, a ton of different types of problems depending on the boundary condition. In the Fokker Planck equation, you can also add the force field, for example, that you don't have in the diffusion equation. So similarly, what you want to do if you have anomalous diffusion, which is still in some sense universal because it's related to Levy, you want to build a set of differential equations that describe it. But it's obviously not the ordinary diffusion equation because that gives you Gaussian statistics. And secondly, we showed that there is some memory in these continuous time random walks, which means that the local move is not depending what exactly is happening at this moment of time. So in an ordinary random walk, let's say with Poisson waiting times or something like that, the probability of making a jump at any given time is the same. The time is really translation invariant. But in continuous time random walk, after you make a jump, then you draw a new random variable from a new waiting time, let's say with a power law distribution. So you remember when you made the previous jump at least. So there is a memory. And this memory is related to this fractional derivative. So let us see what is it about. Let me start. There's no over there. So so first of all, let me remind you what is the Fokker Planck equation, the ordinary one. I have a density of particles. This is normalized. So this is the probability to find the particle at position x at time t, starting from some initial condition. It changes with time. And then I'm going to write here some diffusion coefficient k1. And then I have a Fokker Planck operator acting on the density, and I'm writing it in one dimension. So this is the Fokker Planck operator. This k1 is usually d, the diffusion constant. But now d is still going to be the derivative. So I use k1 instead of d. So this is just the diffusion constant. And if the external forces are 0, so this is a force field. If this is 0, then the Fokker Planck equation, the Fokker Planck operator is simply the second derivative with respect to x, and then this is the diffusion equation. But more generally, we can have a force field which is not 0, then the Fokker Planck operator is composed of two terms. One of them is describing diffusion. So this is the action of the random walk. You could jump evenly left and right with equal probability, and then you get the usual diffusion equation. So this is this part. And then you can have also some drift because of a force, and here you'll have k Boltzmann t. So, but for our purpose, for this class, you can forget about the force for the beginning. I'll just mention it a little bit in the end. So we have only this. In your homework assignment that you need to give me, so I'll repeat what I said in previous class. For the mid-semester, you need to solve one more kind of exercise, which is slightly larger than what you had up till today. You do it like an exercise. In it, you'll have this equation, and then you'll treat the case when f is a constant. So this is one part of your assignment. The second part is to summarize an article and expand on it a little bit and give it as a work. Okay, so you have these two assignments. And again, you'll see this in your assignment. So, but for today, let's say this is 0. So you just have diffusion equation. Okay, is this clear? Is this notation clear? Is it unclear? Is it clear? Okay, Lior says it's clear, so it's clear. Okay, fine. So we have this description. We all know this. For example, if I take x and I multiply and I integrate over all the positions in space, Then I get, here I'll get the derivative of x average. And this will be given by K1, K Boltzmann T, the average if f. And if f is a constant, then this is the mobility, and then you see K1 divided by K Boltzmann T. This will give you the relation between diffusion constant and mobility, the response to an external field. That will give you the Einstein relation, etc. And also we know that if you have an equilibrium, which means if the potential is binding, so this force has some potential, let's say harmonic potential, then in the long time limit, you get Boltzmann statistics. And this is why we have here this K Boltzmann T. So this K Boltzmann T just means that I'm working close to thermal equilibrium, and then I'm demanding a thermal equilibrium on the system, so that you have to have here this force in order to reach this final state in equilibrium. And if the force is 0, then, and let's say you start with a delta function, then of course you have these Gaussian solutions, which are well known. We know everything about this equation. Now, to introduce the fractional equation, so what I'm going to do now, I'm just going to tell you what is the fractional equation, and then we will, at the end, we will go back and explain why this makes sense at all. By the way, in this business of fractional derivative, it's a zoo. The reason why it's a zoo is that there are many ways to generalize the fractional derivative. There's not only one way to say, okay, I can invent some fractional calculus. You can go home tomorrow if you want, and you can invent some fractional calculus, some rules. So different mathematicians invented different rules. And you need to know which are the clever rules and which are the stupid rules. So there are many pitfalls. So when you read the literature, it's a bit of a mess, and people have to work and think hard which type of derivative is the correct one. Because to generalize something, you can generalize it in many ways. And it turns out that the relevant calculus is due to Riemann and Liouville, which were great mathematicians, of course. Their calculus eventually turned out winning in this context. It doesn't mean that other fractional calculus don't exist. They exist, and maybe they have different applications. But Riemann and Liouville are going to win in our context. So we are going to discuss a particular type of fractional and integral derivatives. And in fact, what you need to do is not just say, okay, here I have some t to the alpha and think what it means, but actually what you need to do is the first step is turn this equation into an integral equation. And that means I just integrate over time. So if I integrate the time derivative over time, I guess I get this one. This is the initial condition. This is what I'm after. And then I have here K1. The Fokker Planck operator does not depend on time, and here I'm going to write an integral pxt dt. So I just integrated both sides of the equation, and now I'm going to write this. Usually, first of all, at first this looks strange because integral equations usually are considered more difficult than ordinary differential equations. But soon you'll see why. When you go to the fractional derivative, then you'll see why this is the correct way, and it's related actually to the initial condition. We want to preserve the initial condition. Because let's say I put here t to the alpha in some way. Then the first question is, what are the initial conditions of an equation? Let's say I have here alpha and alpha here. What are the initial conditions? If you have a first order derivative, you know that this type of differential equation are solved by one initial condition because you have the first order derivative here. But if you have your alpha, so what does it mean? How many initial conditions do I have? if alpha is, let's say, half, what does it mean at all? So what we do here at the first step, we put the initial condition here, and then it's very clear that we're going to use this initial condition, and there's going to be only one initial condition, even though the equation is going to be here. Eventually you'll have, in some sense, t to some power alpha. So let's see how you do it. First of all, I'm going to rewrite this in a strange way. Here I'm going to use an integral operator. So this is an operator on x, second derivative in x, for example. And this is an integrator over time. And in it, I want to write this integral like that. So what does this mean? This integral is from 0, that's the lower bound, till t. And it's 1, because it's just one integral. It's an integral of order 1. So I can write it like this, and then I can say, okay, I'll just give you the result. Well, it's not really giving you the result. What is the fractional Fokker Planck equation? The same thing, but here I have some other type of diffusion constant, which depends on this alpha. Here you have the Fokker Planck operator, which is the same Fokker Planck operator. And here I have it to the power alpha p. This is the px and t, if you want. This is the fractional Fokker Planck equation. Of course, we need to explain what is this operator. But what I did here is actually take the integral and I generalized it to some alpha integral. Okay? What is that? Let's write it explicitly first of all. Pxt minus px0 is equal to k alpha times, here I have some gamma function, which is pretty annoying, but it's always there. Integral from 0 to t, the Fokker Planck operator, pxt prime, t minus t prime to the power 1 minus alpha dt prime. So here I explain what is the meaning of this 0t I alpha. You see, it's an integral from 0 to t. These are these two limits, 0 to t. And this alpha enters in a very particular way, like here. First of all, here alpha is between 0 and 1. So what does it describe? You have here the density. You have here the Fokker Planck operator operating on the density, but you also have this object. This object is called the memory kernel. And what does it tell you? It tells you that the density at time t on the left-hand side of the equation depends on the density in its previous history. So you have here a memory, and the history is weighted by this memory. You see, the further you go backward in time, you have less memory because this shrinks. And of course, when alpha is equal 1, then there's no memory at all because all this goes away. Of course, I'm just giving you this here ad hoc now, and we want to explain why this is actually an integral at all. I mean, a fractional integral, in what sense? And how is this related to anything in physics? Sometimes people now do the following. They take the derivative in time of this equation, the ordinary derivative, and if you have an integral of order alpha, and you define the derivative on it, a usual derivative, so you have here alpha minus 1. So in some sense, if I have an integral which is alpha minus 1 and alpha is bigger than 1, then I can say this is a derivative of order 1 minus alpha. again, I'm changing the order, so it's the inverse of this. 1 minus alpha t px on t. This is another way to write this equation. This derivative here is called the Riemann-Liouville derivative. Fractional derivative. So you can write the equation either as an integral with a fractional order integral or with a fractional derivative, but it's actually on this side.
How is it the derivative?
What?
When you differentiate by t,
The definition of the integral.
integral disappears. You have only
No, because you have both this, and it's very dangerous because when you take t down here, you get a divergence.
Yes.
We will talk about this.
okay.
You cannot just take the derivative up here and down here because here is t minus t.
So,
The definition of a derivative here is 1 minus alpha, but here it's alpha is like this. It's d dt, sorry, 1 minus alpha, I 0 t to power alpha. So you see the minus alpha is like doing the integral. And then the one, the ordinary derivative is this d over dt. So I switch the sign from minus to plus. This is all now a little bit vague, or maybe a lot vague. So now we want to explain this. What does it mean? So again, we start at least with the fractional integral. Let's say acting generally on some function z of t. This is equal to the integral from 0 to t. Again, this is 0 to t. This is this limits. zt prime t minus t prime 1 minus alpha dt prime. And we have the gamma function. Again, this is a definition. So now let's talk about math a little bit. Why do I call this at all an integral even? In what sense is it an integral? Of power alpha. So it's about the name. Why do we call this an integral of order alpha? You can see the following. So let us look now about something you know. An integral of order n of some function f. This I'm going to define the following way. Integral from 0 to t. Integral from 0 to t1. Integral from 0 to tn minus 1. And here I have f of tn dt1 to dtn. So I take a function and I integrate it over dtn up to tn minus 1, then I integrate over tn minus 1, etc., 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 up to dt1. This is what I mean here by n integrals of this function. You can take this. This is a basic and natural definition of this object when n is an integer. Now we want to make the following claim, that this integral I can write also in a different way. I can write it. What? You know the answer? You good? So Leo knows the answer. I'm happy. So this you can write as also as t t to the minus tau and minus 1 f of tau. Again, you can start with this one or this one, whatever you want. It's the same thing. This is the nth integral. In case you are not like Leo, let's say you don't remember that this and this is the same, let us easily check it for 2. For 1, it's trivial, because then you have this goes away, and then you have only one integral. So let's see. Just checking it very quickly as a reminder, f of t. So by the second definition, this is n equal 2. This is the integral from 0 to t, t minus t. I just plug in n equal 2, f of t, dt. This I want to call b of t. B because it's the second definition. And from the first definition, just write 0 to t dt 2, 0 to t 2 dt 1, f t1. And let's call it a of t. We want to show that a and t of t and b of t are the same. So first of all, we know that a0 is equal b0, because both of them are equal 0. If I integrate from 0 to 0, then they are the same. Then the derivative of this function, then it's very easy to do, because when I take the derivative now, t minus t will be 0, and then I need to just take this derivative here. So I'll just get, this is just the integral from 0 to t, f of t dt, and b of t. You see, I just take the derivative, t appears only here, so I need to replace this t2. It's the same thing, that's the point. And of course, a second derivative is then ft, and that is equal bt. And then all the derivatives are the same. These functions are analytical, so I can expand them, and then that means that a is equal b, which is well known and trivial. So my point is very simple. I can represent integrals in either of these two ways. Now you understand what was actually done here. What is this fractional integral of order alpha? I simply replaced this n with alpha, that's all. You see here. Here I have 1 minus alpha, so I can take it downstairs, and then minus alpha, this n will be alpha. And of course, I need some clever way to generalize the fraction, the factorial. So this I do with this gamma function. You can claim this is not unique, that's fine, but this is how Riemann did it. So what is this thing? What is this object? Let's say on a function f of t. This is the same definition that I gave you before. This is this gamma alpha. And here I have t minus t prime. Here I called it t prime, but let's call it tau like here. And here I have alpha minus 1 f of tau d tau. Okay, so now you know everything on the definition of a fractional integral. Again, alpha here is between 0 and 1. And again, I said this already, but let's repeat. If I want to have a fractional derivative, I define it through the integral with an additional derivative. So this is equal d to power n dt to power n I 0t n minus alpha, and n is plus 1 alpha is the whole part, the floor of alpha. But in our case, it's very easy because alpha is always between 0 and 1, so n is equal 0. So n is equal 1. In our case, n is 1. But you can define it more generally with an n. Again, there is a choice of definitions here, and we will soon see why this definition is smart. Okay, so let's do an example. Where is this? So let's take the derivative of order half. So this is a half derivative of the simplest function you can imagine, which is t itself. So we just plug it into this equation. So we have the following. We have 1 over gamma to the of half. This is this gamma function because alpha here is half. So alpha is half. And then I have an integral from 0. First I have the derivative. This is this derivative. N is equal 1. So here n is equal 1. This is the derivative, this one. Now I need to do the integral. The integral I defined here. This is simply equal, here alpha is half. Half minus 1 is minus half. So here I have t minus tau. And the function itself, this f, is t. So I have here tau half d tau. Again, I cannot just take the integral, put this inside, because I'll have a divergent. But in this case, at least, I can solve this exactly. I can switch variables. Let's call t minus tau. Let's call it minus y. And then you'll have here y downstairs to the power half. And upstairs, you'll have here y plus t. This integral is super easy to do. Then you'll have 1 over gamma half. The first order derivative. This turns out to be 4 over 3 t 3 over 2. And then this is equal, I just take the now ordinary derivative. This is equal t to the half, because if you have t to the 3 over 2, I take the derivative, it's t to the half. It's 3 over 2, this gives you 2 over gamma. And this is like a square root of pi or something like that. So the important point here is I took the derivative with respect to half of t. This is t to the power 1. This is a half derivative. 1 minus half, because this is the derivative, gave me this half. This is what you expected based on intuition, that a half order derivative of t will give you t to the half. And the prefactors are just given by this gamma function and some other prefactors. Now, there is a fundamental difference between this calculus and what you studied up till now, in the following sense. Usually, how did you start studying calculus? You learned it from geometry. So you have a function, and then the derivative of the function is the slope on some point, etc. And the integral over the function in one dimension gives you the area underneath this curve. This does not exist here, because you have this memory effect. So there's no simple geometrical interpretation, but there is a memory that goes back in time, that you memorize something. And for system memory, this becomes important, and this is what we use here. So now let's do this, the same thing, and see again what is this derivative slightly more generally. So another way to look at this, what is this integral after all? What is this integral? It's a convolution. You have a convolution of the function z of t, or here f of t, with this memory. And if it's a convolution, then in Laplace space it's going to be a very simple and elegant form. So another way to see this is the following. Let's go to Laplace space. Let me do it with another kind of an example, but you'll see that it's much more general. So let us take the derivative with alpha of some function now t to the power mu, something more general than what before we had alpha equal half and mu was 1. Now we want to do it slightly more generally. So I just need to, again, use this equation. Alpha is between 0 and 1, so I need to take, I have here 1 over gamma alpha. I have the derivative. This is this derivative. This n is equal 1. And now I have to do the integral with 1 minus alpha. So I have this integral 0 to t. I made a mistake, but tau to power mu, t minus tau to power alpha, d tau. And here I have 1 minus alpha. This is because this guy, you see 1 minus alpha, so alpha is 1 minus alpha, so I have 1 minus alpha. Now we want to do the Laplace transform. This is not Fokker Planck operator, so this is the Laplace transform. Of everything, dt alpha t to the power mu. By the way, once we get this result, then let's say we have a function, cosine t. You want to take the derivative of cosine t. What do? You expand it in a Taylor series up till infinity, and then you take term by term derivatives, and then you have the derivative of the function. So any analytical function, once I know this derivative, I can take the derivative of by a series expansion. So we want to take the Laplace transform. So when we have the Laplace transform, then we will get something maybe easier. So the derivative of d of t, this is some function, is the function itself, and there's the initial condition, but if you put here t equals 0, we interpret it as 0. So here I have this s. This comes from here. This was already in the class several times, that the derivative, the usual derivative, goes to Laplace variable s. So here I will be jumping all the time between time and s. Time is real time, s is the Laplace variable corresponding to t. And now I need to take the Laplace transform of this convolution. This is also easy because this will be simply a multiplication of the Laplace transform of this object and the Laplace transform of this object. But the Laplace transform of this object or this object, I mean, not with t, but with tau, is very easy to do because this is just Laplace transforms of t to power something, beta or alpha, it's the same thing. So let us just write it down. For example, t to the minus alpha, it goes with s minus 1 minus alpha, gamma 1 minus alpha. So this is the Laplace transform of this function, is s minus alpha. You remember when you do the Laplace transform, you integrate over dt, e to the minus st, then you can look at the units. And this is how you easily remember this, and then you need to remember this gamma function that comes from the Laplace integral. So this will give you the Laplace transform of this guy will give you s minus 1 minus alpha. And then I have, it's the same thing actually, tau to the to plus u mu this will be s minus 1 plus mu. See, here I have minus alpha. Now I replace the minus alpha with mu. That's all. And here I'll have gamma 1 plus mu. So this guy, I can write it down now as gamma 1 minus alpha times s. This was from the derivative. And then I just need to copy. It's like being an accountant. S minus 1 minus alpha, gamma 1 minus alpha, S minus 1 plus mu, this one, gamma and you see this gamma now cancels. This is maybe the reason why Riemann put this gamma here. And then you have s minus alpha, so you get a simple expression in Laplace space. This is equal to s minus 1 plus mu. Here we have minus minus, so it's plus alpha gamma 1 plus mu. This I can write slightly nicer. But this is again easy to do because I can now go something similar to this, go into real time. But let us see what we did up till now. You see what is going on here really. You see t to the power mu goes with this s minus mu thing. This is the Laplace transform of tau to the power mu, right? This part. And then I multiplied it by s to the alpha. And this is a perfect sense. What does it mean? It means that the fractional derivative of order alpha in Laplace space, you just take the function and you multiply it by s to the alpha instead of s. So d to the power alpha of some function goes into something like s alpha, the function of s. So if alpha would be 1, this would be perfectly sensible. This would be the derivative in Laplace space. Now you have alpha, so it's some number alpha less than 1. So this is this alpha here. So, and similarly for the integral. What is an integral in Laplace space? Is instead you can look at an ordinary integral. If I didn't have this alpha, that would be like in Laplace space it would be multiplying the function by 1 over s. So in Laplace space these fractional derivatives make a lot of sense. It's just a continuation of Laplace from integers into the fractionals. By the way, you can have the same thing with Fourier transforms. So you know that Fourier transforms, you know, for example, the first derivative of a function in space corresponds to minus ik or ik in Fourier space. Or the second derivative in space corresponds to minus k squared. This is also done by another mathematician called Cauchy. I think all of you heard about Cauchy. These are called Cauchy fractional derivatives. So you have a fractional calculus based on Fourier. There is a fractional calculus based on Laplace. Laplace goes with Riemann and Liouville, and Fourier goes with Cauchy. This is because Fourier and Cauchy were both of them French. No, not really. But this is how it works. So there is more than one definition of fractional derivatives. For example, if you want to do Levy flights in space where you have long jumps instead of long waiting times, then you use instead of the second derivative in space of the diffusion equation, you use a fractional derivative in space, but that is related to Fourier, and that is related to Cauchy. Again, I'm just mentioning here briefly that there are several ways of defining these fractional derivatives, and you need to be careful what type you use, and why we choose to use a particular set of them is important. Anyways, we got here this derivative in Laplace space, and now we can easily invert it. So the inversion is exactly the same thing like we do here. So I can summarize this. And I can just write down the solution. So the derivative to the power alpha of t to the power mu is equal to this. Of course, if you have your integers, it also works, because then these gamma functions turn into factorials. And if you ignore for a second these gamma functions, what you have, the fractional derivative of order alpha of t to the power mu is t to the power mu minus alpha, which again makes sense, because usually we are used to, you have here mu, and here you have, let's say, 1, then you'll have mu minus 1. So now we want to go back to physics. This was just math. This was invented, I don't know, 300, 400 years ago. And you can do much more than what I did here. You can define fractional differential equations. This was done. There's a whole field of math that deals with this. We're not going to do it. We are going to discuss only the fractional diffusion equation. So the fractional diffusion equation is this. See, then the density that I'm interested in minus the initial density at time t equals 0 is equal to the diffusion coefficient k alpha. K alpha has units of meter squared divided by time to power alpha. So it's an anomalous diffusion constant. K1 would be the usual diffusion constant, but here we have something else. This is times this gamma function, integral from 0 to t. Here I have the Fokker Planck operator, and I'm taking here only the second derivative in space. So the force is 0. This is the so-called fractional diffusion equation in one dimension. Fractional time, sometimes it's called. Because again, I can change this to get these Levy flights if I wanted to. And here I have t minus t prime 1 minus alpha px t prime dt prime. So this is like in the ordinary diffusion equation, the second derivative that is causing this diffusion. And here I have the memory that goes back till the beginning of time, because I integrate here from 0. For example, what is, let's say that you start px at time 0 with a delta function. And then we ask ourselves, what is x squared? We know what's x squared. X squared goes like t to the alpha, but let's do it. So when I multiply by x squared, I just multiply this equation by x squared, and I integrate over x. So then I get the following. I get here x squared. Here, because of the initial condition, x squared times the delta function integration gives you 0. This is k alpha, gamma of alpha. Now I need to integrate over all space dx over x squared, because I'm calculating the second moment. Here I have the second derivative. And I have the integral over time. What I did here, what I'll do here, I'll first do the derivative in space. Now, here we're going to use a very simple trick, which we did many times. We're going to integrate by part with respect to x. So if I do that, then instead of getting, and I use the boundary conditions so that far away the solution is 0, this all can be proven. We don't prove this, but this is of course correct. And then when you take the spatial derivatives, then you get here, you simply get here integration by part once, you get 2x, and then another time you get a factor of 2, and then you have dx over the density. And one can show it. This is really easy to show that this is equal 1 for every time t. Which just means that the density, the normalization is conserved. You don't lose particles here. This is trivial. You just integrate this here. You get something, and then here you have 1. You do integration by parts, and you can show that this conserves normalization. So eventually what you get here is, you get here x squared equaled k alpha times 2. This 2 comes from this x squared. Gamma function, integral from 0 to t minus t prime, 1 minus alpha dt prime. And this is a trivial integral. This is equal to, from here I get another alpha that will change the gamma function into the following. 2 k alpha, here I have gamma 1 plus alpha, and here I get t to the alpha. What does this show us? It shows us simply that from this type of fractional diffusion equation you get anomalous diffusion. That's all. You can do it in many different ways. But now let us see a slightly deeper why this equation is actually the continuous time random walk in disguise. Anyone has an idea how to do that? Why is this? How should we relate this equation to the continuous time random walk? What is the usual trick? The usual trick. Any ideas? I want to show that this is like the CTRW. What shall I do? First of all, what does it mean like the CTRW? It means that if I take the continuous time random walk and go to the long time limit, this is the description. Similar to ordinary random walks that in the long time limit are described by the diffusion equation. That's the Laplace, and you are half right, and the Fourier transform. So the idea is simply, we saw already that all these fractional derivatives, they are very easy to handle in Laplace space. And also we have here the second derivative, which we know it's much easier to work in Fourier space. And then we're going to take the Fourier Laplace transform of this object, and we will find the solution. And then we'll compare it to the solution that we get from the continuous time random walk, and the surprise or not surprise, it will be the same thing. So this equation is the long time limit of the CTRW. And again, the goal, this is again, this is written in many different ways in the literature, for example, like this. And again, the goal here is we have this equation, then a later stage, maybe we can add all kinds of boundary conditions, etc., to solve this equation. So let us see this. So first of all, again, let us take px at time 0 as a delta function for simplicity. But we can take any initial condition in principle. And we take the Fourier Laplace transform. So x goes to k, t goes to s. So here I have p, k, and s. And the Fourier transform of a delta function is 1. And then the Laplace transform of 1 is 1 over s. And then I have here the following. I have on the other side, I have k alpha, gamma alpha. This is this one. And then I have minus k squared. This is this second derivative with respect to x turns into minus k squared. Of course, here I get p, k, and s. And this is a convolution. You see, this is again a convolution. So here I get s to the minus alpha. This is from this term. Again, this equation was already on the blackboard, that if you have t to the alpha minus 1, then this is the Laplace transform. And this is multiplied by gamma of alpha. So this comes from here. These two guys cancel. So what do I get? I get, and let's multiply by s to the power alpha. So I get the following: s to the power alpha, pk of s, minus s alpha minus 1, minus k alpha k squared, pks. I can take this one to the other side and this guy to this side, so pks in Fourier Laplace space, okay, it's here equal s alpha minus 1 s to the alpha plus k alpha k squared. What is this object? This object is the solution of the fractional diffusion equation in Laplace Fourier space. If I can do the inverse Fourier Laplace space, I can solve this problem. We already did this inverse Laplace transform when we saw the CTRW, but I want to remind you I'll remind you that this is the solution of the CTRW, and I'll identify what is this k alpha exactly. So what did we say in the CTRW? So here we have some psi of tau, tau minus 1 plus alpha. So first of all, I identified the fractional derivative that was invented by Riemann a long time ago with the power law tail of the waiting time PDF. This alpha and this alpha are the same thing. In CTRW, we have a non-biased jump length. It doesn't really matter what it is. It can be on a lattice. We assume that the jump length has all the moments exist, etc. So we are not talking about Levy flights. We are just talking about, let's say, a PDF of jump lengths, f of delta x, something, let's say, Gaussian. Why is it important to assume no bias? Because I'm just talking about the diffusion equation. There's no bias in the diffusion equation, so I'm choosing a jump length PDF that behaves in this way. So in these cases, psi of s, we are going to assume more specifically is 1 minus a s to the alpha. A is some coefficient determined by this amplitude here. So this is the Laplace transform of S, and then there is a Fourier transform of f of k, which is the jump length distribution. After you wait, you jump. And this is given by sigma squared k squared over 2. And what is this sigma squared? Sigma squared is the variance of the microscopical jumps. So we have here two parameters, a and sigma, and then we have also alpha, of course. Then according to the Montreux-Weiss equation, which is the solution of the CTRW, you have this object. So here what we did is we looked at the CTRW propagator in Fourier Laplace space. And we had the possibility of jumping 1 time, 2 times, 3 times. We looked at the probability of making these jumps, and we had an infinite series, and then this gives us this geometric series, and then you have 1 minus fk psi s. And this was given by the probability of not moving at all. All this again was in the classroom. And then what we said in the long time limit, I can approximate this by the small s, small k approximation corresponding to long wavelength and low frequency, low frequency limit of this thing. So then I have 1 minus psi s. This is a s to the power alpha divided by s, this s. And here I add 1 minus sigma squared k squared over 2. Here I have 1 minus a s to the alpha. And when I pick up only the leading order terms, so this CTRW propagator, here it's only asymptotic, and the small k, small s, corresponding to large x and large time limit. This is a s alpha minus 1. You see I have 1 times 1 is 0. Here I have sigma squared k squared over 2 plus just leading order terms I'm taking here, a s to the alpha. And this I will tidy a little bit. This is s to the alpha minus 1 k squared times sigma squared divided by 2a plus s to the alpha. So what is this k of alpha, this diffusion constant? It's simply given by this sigma squared over 2a. What did I do here? I just looked at the asymptotic limit of the CTRW like we did before, and then I get this coefficient and I compare it to this, and you see it's the same thing, which means that in real space, real time, the solution of the CTRW and this fractional diffusion equation are the same thing. where I identified the anomalous diffusion constant. And you see that this relation, K alpha is sigma squared over 2a. It's similar to the Einstein relation, but different. What did we have in the Einstein relation? Well, first of all, alpha was 1, and here a was the average time between jumps. But upstairs, we had the variance of the size of the microscopical jumps. Here we have something very similar. We have the variance of the size of the jumps divided by a. And a is this coefficient here that describes the far tail of the PDF. It replaces, in some sense, the mean time between jumps. And we know already that this a is controlling the dynamics in the long time limit. So this is a generalized Einstein relation, and this equation is the generalization of the fractional diffusion equation. So now in your homework, you'll have a few questions on this topic. Hopefully you will get familiarized with these fractional derivatives. You play with them a little bit, and you just learn, and you know that they exist, and they are useful, because there are many applications of, today there are already, the last 20 years, there are several applications of these fractional derivatives in physics, but I would say these are not so well known. For example, it's very weird that when you study derivatives, you don't study these fractional derivatives, because maybe that's the reason why this field was blocked in physics, and it took so long until it was discovered that it is useful as a mathematical tool to describe physical phenomena. What other physical phenomena is described by this? So you know we have Langevin equations. These are stochastic differential equations that describe motion of particles in a randomized fashion. They are related to these Fokker Planck equations, but then there's also something called fractional Langevin equations, which means that instead of taking the fractional derivatives acting on the propagator, we can take the fractional derivatives and they will act on the trajectories themselves, like in the Langevin equation. Like in Langevin equation, you have, for example, the first derivative of velocity is minus gamma. Gamma is the friction times v. That's Stokes' law plus some Gaussian right noise. So instead of taking the derivative of velocity or the velocity, you can take a fractional derivative. And that will describe memory in the path itself. So it's a very broad field. This is only, I just showed you here a little bit of it. These fractional derivatives are very useful in many descriptions of all kinds of things, like weak ergodicity breaking and et cetera, et cetera. And it's more or less still active field, even though now I think it's starting to decline. It was popular, and then people use it less now in the last 5 years or so. Okay, so here we will stop. We'll have a break. I'll go get your exercises, and please hand in the CTRW exercise, the last exercise you have to give me today. And those of you who did not think about the project, maybe you think about it now in the break quickly, and you tell me what you want to do. Okay, so some of you already chose, and we already discussed a little bit this issue of weak ergodicity breaking. So now I'm going to discuss this from very one specific point of view. So I already gave you the philosophy last class when we discussed this on the blackboard. Time averages are not equal to ensemble averages, etc., etc. But the goal now will be more mathematical, to derive some result, one out of many results, and show you how this works. So recall that blinking quantum dots. So in a phenomenological way, we have some intensity as a function of time, and then you have this on-off sequence. And I showed you some experiments even, where you have some intensity, which I'm going to call 1, and some other intensity, which I'm going to call 0. Now, of course, in the real experiment, there's some noise here and some noise here. So what we're actually doing here, we're defining on the real experimental data, we're defining a threshold, and then we define everything above the threshold as on and everything below the threshold as off. And then the interesting thing was that under certain conditions, we had psi of tau equal tau 1 plus alpha. And alpha in the experiments was close to half, but I'll do it in general. Alpha is between 0 and 1. So, and of course, there are many variations of this, because you can have power law distributions in the on state and not in the off, and vice versa, all kinds of games. But at least for the blinking quantum dots, you had power laws both for the on and for the off, at least within a long time interval. And this created this very strange landscape where, because there's no scale, the averaged waiting time in these both two states is infinite. Then what you get is that as you go by in time, you'll see bigger and bigger events. So here you see some small off times, and then a bigger one, and then even a bigger one. And if I continue the experiment over time, I'll see even bigger and bigger guys, because the average of tau is infinite. Now, why is this related to weak ergodicity breaking? So we have in mind the following standard stochastic dynamics. So let's say that you have another sequence of blinking on off. But let's say that the distributions, this is, I just calculate how many odd ones I have, how many even ones when n is this number, and you get the following expression: psi s plus u to the power k plus 1, psi s to the power k, minus psi s plus u to the k plus 1, psi s to the power k plus 1, all this divided by s.
You want psi k instead of psi s. Oh.
Here k psi s. Thank you. And you more or less can see this. You see the difference here is the Tn plus 1. This gives you this k plus 1. And otherwise, these are simply, this comes from the odd ones, this comes from the even. K plus 1 plus k is the total number. And the 1 over s is this 1 over s. Now you need to do the same, and it's not exactly the same. There's a little bit of trick here where you are even, that you end up there. And then you do the same. I'm not going into the detail. And then you need to sum over all the k's, both when you have an even number of transition, like the case we did not do, or odd number of transitions. And if you do that correctly, okay, of course, this can be simplified. This is psi s to the power k, psi s plus u to the power k. This is k plus 1. And this is equal 1 minus psi s over s. If you do this correctly also for the, when n is even, and then you sum up over all the k's, you get the final result. I'll just skip to the, it's a simple geometric series you see from here. Something similar to what we encountered before. We get the following exact expression. So the PDF, again, this is summing over n slash k. The PDF, when you start state plus of at time, not at time t, but at Laplace variable s, so s goes to t, u goes to t plus. So I already summed over all these n, so I don't have an n anymore. This is equal to the following very nasty equation. From which is very difficult to learn anything. And you see, we calculated this guy. This guy is when the number of transition is odd, but here you have this s plus u, which replaces this s, and this is because the last guy is a bit tricky. So I'm not going into the details. You can go over them, or you can do this as an exercise. Good Russian look. The question now is, okay, what do you learn from this horrible expression? Let's get something trivial out of this. So what we do is we take the limit s to 0, u to 0. This corresponds to t to infinity and tau plus to infinity. Actually, to be more precise, the ratio is going to be finite. So I'm going to look now only in the long time limit. And again, we did similar things for CTRW, so it's like taking the small k, small s from the CTRW. Now I'm doing it the same thing, but I'm doing it in Laplace space. And let us assume that psi of s is equal to 1 minus s times the average of tau. This is a normal behavior. In what sense it's normal? The average is finite. This is what you expect. What I'm going to get now is going to be trivial, but let's see how it works. So I use this PDF. I started at 1 and I said it's not so important, SU. I simply take the expansion. So I take 1 minus tau average s plus u. Sorry. Just plugging it in here. So 1 minus psi s is s average tau. So here I have s plus u, which is small, times tau. So here I have average tau. Here I have, again, average tau, and this is 1. Here I have psi u plus s times psi s. What is this thing? Psi u plus s psi s is roughly u minus average of tau s plus u 1 minus s tau. So this is equal 1 times 1. This is of course 1. Here I have minus 2 times s tau, and here I have another one from this times this, minus tau times u. Now I need to take 1 minus this. So all this is multiplied by 2 tau s plus tau u. And here I get the following. You see here I have 2 tau, here I have 2 tau. So this is equal to s plus u over 2 like this. This, if you translate this, the PDF of t plus is simply a delta function on t over 2. You see here that the tau went away, and this is exactly what you expect, because you expect half of the time to be in a state up. That's why, and half in the state down, and then t plus is t over 2, and that's related to this 2 that you have here. Now we want to do something slightly different. So if tau is infinite, then psi of s is 1a s to the power alpha. Again, I use this equation. So I have 1 minus this thing. So I use the following: 1 minus psi s is a s to the alpha. 1 minus psi s plus u is a s plus u to the power alpha, etc. I plug this in. Here I have 1 times 1 will cancel this 1. And if I do that, I get the PDF starting at 1. It's u s is proportional to, in the small s limit, this nasty equation. So you get an expression which is nice because it's independent of a. A cancels out. A cancels out is exactly like before, that the average tau did not appear in when you have half of the time you're up, half of the time you're down. It doesn't matter what is your average tau. Also here, you don't get it, but you see here that, you know, to invert this is not so easy. When alpha is equal half, you can do this by some special integral. However, already 40 years ago or so, people were able to invert this. And I'll just give you the final result of the inversion. So what's the solution? So again, this is the generalized arc-sine law. First of all, what you see, because you have s and u, you see that this t plus is scaling with t. There is a kind of random variable in front of it. And this is related to the fact that I can define a new random variable, p plus, which is t plus divided by t. And this random variable is, of course, as I said already, is between 0 and 1. And if you invert this, you get the following. The PDF of p plus is this distribution. It has a lot of structure. This distribution has a name. It's called Lampretti distribution. This is the PDF, but this is Lampretti distribution. The exact form is not so important for you guys. The question is, how does it look like?
What is P bar?
P bar, I said. P bar, okay, P bar is this. T plus over T. And of course, the minus is the same thing.
So the T there, all the T's are P bar?
Yeah, yeah. This is the random variable. The special case alpha equal half is what Paul Levy found. That's the arc-sine distribution. So how does it look like? So I have a PDF of P plus. Let's say alpha goes to 0. Then you can use this equation. First of all, P plus is between 1 and 0. This distribution looks something more or less like this. This is also a trivial result. It means the following. If alpha goes to 1, let's say it's 0.0000.1, either all the time you are in state up, or all the time you are in state down, and then P plus is either 1 or 0, and then you have this very U-shaped line. When alpha is roughly half, you have a structure which is not trivial. It looks something like this. And this is the famous, this is what I told you before, this arc-sine law. So you need to just plug in here alpha equal half. You get some expression. If you integrate it, you'll get the arc-sine, and that's why it's called the arc-sine law. If alpha is, let's say, 0.8, you get something like this. All these functions are symmetric, so the average is always half. This is because the up and down were chosen to be the same, so the average is half. So this is symmetric around the half, as it should be. This is also symmetric, even though my plot is not so good. And what you see here, you see that when alpha is becoming closer and closer to 1, you develop a peak here. This peak, when the average is finite, this peak will be so dominant. So when alpha goes to 1, you always have this delta. You have something even more pronounced. And then if tau is finite, you go back to a delta function, and this is what I call normal case. So there is a transition from this U shape, this sometimes is called W shape, and there is a critical exponent alpha, which I think is, once I calculated it, .5946. So you get a U shape until this exponent, and after that you get a W shape. Of course, when you work exactly at this value of alpha, you will not be able to see this small peak. It will be so tiny at this transition, but you can easily calculate this. So there is a marked transition between the U and the W shape, which you can easily find from this expression if you want to. It's not signifying much because the transition in practice is very kind of smooth. You can see this easily at 0.8, but if you walk at 0.5947, the peak will be so small, it will be so difficult to see it, but it's there. So what I wanted to show you here is that the following, that when we deal with these processes which do not have a characteristic time scale, you are confronted with the following question. These processes are obviously not ergodic. Everyone understands it, I hope, by now. But the theory is not about something is ergodic and something is not ergodic. That's trivial. The theory is about, okay, you have these time averages. The time average, in this case, over a simple observable, or how long you're in up divided by time, that's your total intensity for the quantum dot. What is the distribution of the time average? How big are the fluctuations? And we understand, and this is also intuitive, that when alpha goes to 0, the time average fluctuations are in some sense very big, but also very trivial. It's like strong ergodicity breaking. Either you are here or there. But when you change alpha, you go through a transition where the statistics of the time average is modified from, again, from U to W. And in this sense, we were able to quantify the weak ergodicity breaking, and not only to say there is weak ergodicity breaking, we can say how big it is, because we know the distribution of the time average of this very particular observable and of this very particular model. But it's much more general. You can go and have many different models, and you can look at their distribution. In fact, I gave you this equation in previous class. If you remember, this was on the transparency. You couldn't see it, but this is the same thing as my general equation for time averages when you have only two states. It's the same thing that was in previous class. Of course, previous class we had more than two states. But here I gave you the derivation of the simple model on the distribution of this very particular time average. So if any one of you is working on weak ergodicity breaking, this is related to this particular subject and to the quantification of the variations of the time averages. Okay, so here I'm going to summarize. I hope you enjoyed the course. I hope you will enjoy your project. I hope you learned something. And I wish you all, best wishes for the Happy New Year and also for the exams and semester break. Okay, thank you.